All right, guys, let's get started. So now we'll study motion in 2 and 3 dimensions. Okay. So in the last 2 chapters, we studied motion in 1 dimension. Okay. So here's what we are interested in. So again, what we want to do is give your position as a function of time. So your position is given with reference to a coordinate system. So there's the x-axis, y-axis, z-axis. You are at this location at this time. And how do you get to your location? Well, you travel along the x-axis this a certain distance, then y-axis a certain distance, and the z-axis a certain distance. And that's what those numbers are. And so if you're flying like that, if you give me these 3 functions, then I know exactly where you are at all times. So this is a description of that motion. Okay. And from this description, what is it that you're interested in extracting? Velocity and acceleration. Okay, so you are interested in finding what this is and acceleration. Okay, and so here's the velocity is, it's just like in the previous case, velocity is the time derivative of your position. Okay, so it is d by dt of this guy, xt I plus yt j plus zt. Okay, so it's the time derivative of this d by dt of xt I plus d by dt of yt j plus dz. What do you think we should call this? That's the x component of your velocity. Okay, see, this is a velocity vector. That's the x component of your velocity. What should we call this? So x component of your velocity. Okay, so given your position as a function of time, I know how to calculate your velocity as a function of time. Okay, and when is it that you're accelerating? When do you accelerate? When your velocity changes. Okay, so let's go over here. So you accelerate when your velocity changes with time. If your velocity does not change with time, that means your acceleration is 0. Okay, so we are now taking the derivative with respect to that. So, okay, I'll just write dt Okay, so now if you take a derivative of this vector, the rules are that will become a second derivative, that'll become a second derivative, and that'll become a second derivative. There you go. Yep.
So that first equation represents position.
Yeah, that's the position, your position as a function of time. And yep. Okay, and this is a three-dimensional motion. Okay, so if it was a one-dimensional motion, what would they'll give you only this function. If it's a two-dimensional motion, they'll give you only these two functions. If it's a three-dimensional motion, they give you all three. Yeah.
So given that each of these vectors is described by separate functions of time, does that mean that we would evaluate like the components of motion independently of one another?
Yeah, so the motion in each direction is independent of each other. So if you apply, you'll learn in the next chapter, if you apply a force along the y-axis, you won't affect the motion in the x and y direction. Okay? All right, now I'll give you an example of a motion. Okay? So what I'll do is, so here's the motion. It'll look like this. It's a spiral motion. You're spiraling upwards. Okay, I'll write that function for you. You guys understand? It's a spiral motion. And your velocity along the z direction will be constant. If your velocity along the z direction is constant, what is the acceleration along the z direction? Zero. Okay? So I'll write a motion where az will turn out to be zero. Okay? So here's the function. All right, so at t equal to 0, your z coordinate is 0, your x coordinate is r, and your y coordinate is 0. Okay? And so, all right, so I'm going to draw this motion. Don't worry about the details. So at t equal to 0, you're starting there. And dy by dt is, so that's minus sine omega t. And cosine omega t is, so minus sine omega t. All right, we'll come to that in a second. Okay, so vt is dr by dt, and derivative of this is, derivative of cosine is negative sine, and then you get an omega from there. So minus r omega sine omega t I plus omega r cosine. Okay. So again, at t equal to 0, this is 0, the I component is 0, and this is positive. Okay, so this object is starting here, and it'll have a velocity in this direction and then spiral up like that. That's the motion. Okay. The acceleration is derivative of this, derivative of sine is cosine, and then you get an omega r omega square cosine omega t I minus all right, so here is an example. Yeah. So for this spiral motion, there's the velocity as a function of time, and there's the acceleration as a function of time. Okay, so in a little bit you learn when you're going in a circular path, your acceleration is pointing towards the center, and so since you're continuously spiraling, the acceleration vector is changing, and that's what this is. Okay. What you learn is the velocity is tangent to the path at any given instant. Okay. All right, did you guys understand that? So for 3D motion, when somebody asks you to describe a 3D motion, what is it that they're asking you? They're asking you for this function, and the information you want to extract from that is velocity and acceleration. Okay. Yeah. So that's the general 3D description. We'll be interested in a particular motion quite a bit because we deal with it quite a bit. So when you throw an object, this object, it turns out, is traveling in a plane. This is a two-dimensional motion. When an object travels only under the influence of gravity, when gravity is the only force, then it's traveling in a plane. Now, if you attach a rocket to it, then it can become a 3D motion. Yeah. But we throw objects quite a bit, and so we'll be interested in that. And the second part, we'll talk about that particular 2D motion. Okay? All right. So here's a general 2D motion. Here's a general 3D motion. And when we ask you to describe that motion, what we're asking you is for the position as a function of time. Okay? All right. So now we'll describe the displacement vector. So if this was your motion, this is where you were at time t1, and this is where you were at time t2. Your displacement is a vector pointing from your initial position to your final position. Yep. And that displacement vector is denoted by delta r. Okay, so change in that vector quantity, and that's equal to the vector at the final point, final time, minus the vector at the initial time. Okay, this vector minus this vector is that vector. Yep. So that is the displacement vector, and that's equal to that. Okay, there is the displacement vector in component form, and it's that vector. Okay. We define average velocity. Okay, I'm just defining the average velocity, but you will be interested in the instantaneous velocity. Average velocity is your displacement divided by time. Again, this is a vector, and that's a scalar, so this result is a vector. Which direction is this vector pointing? Let me give you an example. So here's a vector A. Which direction is this vector pointing? Same direction as A. How about this guy? Yeah. So you can see that this vector is pointing in the same direction as that. Okay? Because this is a scalar, a positive scalar. Okay, so the velocity, average velocity vector is pointing in the same direction as the displacement vector. What you'll be interested in is as you take the limit delta t going to 0, so this point is getting closer and closer to that. And in that limit, the velocity vector will be the tangent pointing along the tangent to the trajectory. Okay? So the instantaneous velocity is time derivative of that in the limit delta t going to 0, which is dr by dt. Okay? And as you saw, the x component of the velocity is dx by dt, the y component is dy by dt, and okay? And the instantaneous velocity is pointing, is the direction is tangent to the trajectory. Okay, what is the magnitude of the vector? That's your speed. Well, that will depend on that functional form. That will depend on the functional form of this guy. Okay, you can have different functions giving you different speeds pointing in the same direction. Okay. Okay, so in our example, so for instance, in our example, you see, I could change the speed. The magnitude of the speed is, you take the square of that, it's r omega. By changing r and omega, I can change the magnitude of the speed. So if you take the, okay, so the magnitude of the velocity at any time in our example is r omega square sine square omega t plus r square omega square cosine square omega t plus v naught square. And this adds to 1, so it's okay, so our speed is constant, and I can change that by changing all of those parameters. Okay. All right, so the instantaneous velocity is always tangent to the path. Okay. The magnitude of the instantaneous velocity is instantaneous speed. Its direction is tangent to the particle's path. Yeah. All right, so let's say you're traveling along that path. Here's a motion. At this instant, that's where you are, and there's your velocity. Like I said, tangent to the path. A little while later, you're there, and that's your velocity. Are you accelerating in this motion? I'm sorry? Yes. Looks like the speed is not changing. The direction is perpendicular to the path. Okay? So if both your speed and direction is changing, then you have this component, a component parallel tangent to the path, and then you have, when your direction is changing, you have a component perpendicular to the path. Okay. So let's say if you're driving on a straight road, how can your velocity change? Only speed. So if you're driving on a straight road, you can only have this component of the acceleration. You can't have this component of the acceleration. When do you have this component of the acceleration? When you are going on a curved road. Okay? And so this is called centripetal acceleration. It'll be pointing toward the center of the circle that curve makes. Okay? All right, so here's what you want to remember. So you have acceleration whenever your velocity changes. Your velocity can change by its speed changing. The speed change gives you acceleration tangent to the path. And the direction change gives you an acceleration perpendicular to the path. Okay. All right, so acceleration is dv by dt. And the acceleration is, so x component of the acceleration is that, y component of the acceleration is that, z component of the acceleration is that. All right, by the way, let me write down. So when do you have acceleration? When velocity changes. And acceleration tangent to the trajectory. Perpendicular to the trajectory. When direction of velocity changes. All right, so that's where your acceleration is coming from. All right, now we'll specialize to 2D motion. Okay, so you probably heard this phrase before, projectile motion. Projectile motion is an object traveling where there's only one force acting on it, and the force is gravity. Okay? And that too, we're assuming what is acceleration due to gravity? It's 9.8 meters per second squared with the vector pointing downwards. Okay, for projectile motion, we're assuming that is constant. Okay, so acceleration due to gravity in this room is 9.8 meters per second squared. But let's say if you go 1,000 miles up, it's not 9.8, it changes. So as long as you are throwing objects and lobbing objects, not, distance is small compared to the radius of the Earth, which is 4,000 miles, then you're fine. Okay. All right. So for projectile motion, air resistance is negligible. The horizontal and vertical motions are independent of each other. The trajectory is a parabola. So as long as the acceleration is constant and air resistance is negligible, this trajectory is a parabola. Okay. And we'll show that to you. Okay. So I'll give you an example of a projectile motion and a counterexample. Okay. So I'll toss this. If I toss a piece of chalk, okay, gravity is acting on it, and all other forces are negligible. When I toss this piece of paper, gravity was also acting on it, but the forces due to the aerodynamic forces are comparable to the weight of the object. Those are not negligible. So that's not a projectile motion. Okay. All right, so in your calculus classes, you learned that if the y-coordinate is related to the x-coordinate, if the y-coordinate is a quadratic function of the x-coordinate, that trajectory is a parabola. Okay? And you can see that when you toss a ball like this, the y-coordinate of the ball is related to its x-coordinate like so. Okay? And this guy is negative. Okay, here G is the magnitude of acceleration. There's the initial speed, and this angle is an acute angle, so this is positive. This is positive. And because that's negative, that parabola is pointing downwards. Okay? All right, I will derive this formula for you. Okay, okay. So let's, so the acceleration, so here are the axes. Okay, in this axis, the acceleration due to gravity is a vector pointing like that, and I'll write down the component. This vector has a 0x component and minus gj. Okay, g is the acceleration due to gravity. Its magnitude is 9.8 meters per second squared, and this vector has a negative y component. Okay. So let's look at the x motion. What we'll do is, so what we're doing is we're taking a ball and we're tossing it with an initial speed v naught. So there is the initial velocity vector, and the launch angle is theta naught. Okay. So the initial velocity, v naught, is v naught cosine theta naught I plus v naught sine theta naught j. Okay. So its x motion is okay, there's that equation. We'll toss it from the origin. So this guy is 0. Yep. The x component of the acceleration is 0, so this guy is 0. Yep. So his x position is given by v naught cosine theta naught t. Okay, so what we are saying is you toss a ball with a speed v naught, after time t, he'll be somewhere there, and the x coordinate is given by this guy. Okay, again, we have tossed this ball. After time t, he is there. This is his x coordinate. And let's write the y coordinate at that point. Okay. Okay. Y minus y naught equal to v naught y t plus 1/2 ay t squared. Okay, again, we're tossing him from the origin, so this guy is 0. Okay. So y equal to v naught y, initial y component of the velocity is that. And y component of the acceleration is minus g. Okay. Now what we're going to do is, so here is this y coordinate, here is the y coordinate after time t. What we'll do is we'll solve for t from here, and what we want to do is express y in terms of x. So this tells you t is equal to x divided by v naught cosine theta naught. And we'll put that in here. So y equal to v naught sine theta naught. T is x over v naught cosine theta naught minus 1/2 g times x over v naught cosine theta squared. So you see the y coordinate, you see the y coordinate is a quadratic function of x with this coefficient being negative, which is that guy. And there is the linear term. So as long as the y coordinate is a quadratic function of the x coordinate, then this trajectory is a parabola. That's what that thing is showing you.
When did you get the cosine theta for the x?
Okay, so here's the initial velocity, and the x component of the initial velocity is v naught cosine theta naught. Theta naught is the launch angle. All right, so anyway, don't worry if you didn't follow all of that. What I want you to remember is you toss a ball. This trajectory is a parabola. When is that trajectory a parabola? There's two things that need to be true for it to be a parabola. Yeah, so in this assumption, in this derivation, we assumed gravity was constant and and no other force was acting on it. So since no other force was acting on it, this acceleration didn't change. Okay. All right. Here's the range formula. What the range tells you is the horizontal distance the object traveled when it came back to the same y coordinate. Okay, that's the range formula. So it's not it's the horizontal distance traveled when it's come back to the same height. Okay, so that's the range formula. It's the initial speed square times sine 2 theta naught. Theta naught is the launch angle divided by g. For what launch angle do you get the maximum range?
45.
Yeah, see, and you can see that in this formula. For a given launch speed, this is constant, this is constant. Only if you vary only the launch angle, only this thing changes. And this is maximum for that equal to 90 degrees, meaning theta not equal to 45 degrees. Okay, so you maximize the range when you make this one. And so that has to be 45 degrees. So you get a maximum range for 45 degrees. This gives you the height it reaches, the maximum height it reaches. Okay. V naught square sine square theta naught divided by 2g. When do you get maximum height for a given speed? How should you launch it? Yeah, you launch it straight up. And you see this, that'll be maximum when this is 1. And that'll be true for theta not equal to 90 degrees. Okay. Here's something that most people don't know till they have done a physics course. You see, the range for this launch angle is the same as the range for this launch angle. See, these are complementary angles. So complementary angles give you the same range. Okay. What is the complement of 45 degrees? Fine. All right, so here is the parabolic trajectory. Here is the trajectory of a real baseball. What can you tell me if you look at that trajectory? Soon as it's not a parabolic trajectory, that means there is other forces acting on, which are comparable to the weight of the baseball. Okay? So when you hit a baseball and if it has spin, if you learn that, so if it has spin like this, it's dragging air underneath, faster air moves, lower the pressure. So if you hit the ball with a top spin, there is a downward force. And so for a non-parabolic trajectory, what should happen? Any other forces can't be negligible compared to gravitational force. They're comparable to the gravitational force. All right, now we'll consider a uniform circular motion. What this means is, the uniform means the speed is not changing. And the object is moving in a circle. Okay. So the speed of the object is not changing. Is it accelerating?
Yes.
Why is it accelerating? Because its direction is changing. Okay. So we'll, this car is going in a circle. When the speed changes, what kind of acceleration do you have? Tangent to the path. Very good. If its speed was changing, you would have an acceleration in that direction. But it's not. So you don't have an acceleration in that direction. But since its direction is changing, you have an acceleration that is perpendicular to the path. Okay? So you will have an acceleration, and this acceleration points towards the center of this circle. And so it's called a centripetal acceleration. Okay? Now I'll prove that to you, that the acceleration is pointing toward the center. Okay? All right, so here is this thing drawn. So here, the magnitude of the velocity vector is not changing, and the acceleration at every instant is pointing at the center, okay, from the object. The magnitude of this acceleration is v square by r. Okay? You guys have all experienced this. If you make a turn at a given speed, the sharper the turn, the harder it is to make it. Okay? That's because smaller the radius, greater your acceleration, your tires had better be sticky. Okay? All right. So what did we say? Here we are accelerating because only the direction is changing. And I said this is the magnitude of the acceleration, and that the acceleration is perpendicular to the path, meaning pointing toward the center of the circle. Okay, so I'm just going to quickly go over the proof. You can review this at home. All right, so let's look at this guy going in a circle. Let's look at him there. That's his velocity vector. Okay, so he is at an angle there. So this angle is theta, and this is theta. Remember, the velocity is tangent to the circle, so this angle is equal to that. Okay, so the velocity vector at this point is there is the x component, and that's the sine. So velocity is negative v naught sine theta I, and the y component of the velocity is that which is cosine theta plus v naught Now, we'll look at this triangle, and time derivative of this is Vx. Okay? Vx is this fellow. We're going to put that in there. Vy is this fellow. We're going to put that in there. So there is the acceleration of that guy. All right, if you wanted to find the magnitude of the acceleration, you take the square of that, and there you get the magnitude of the acceleration. Now, to get the direction of the acceleration, okay, so you see, when this is an acute angle, that is positive, that's positive, that's positive. This is positive, this is positive. You see the components, both are negative, so a vector is pointing in the third quadrant. Pointing in this direction. We know it's pointing like that. What I want to show is it's pointing exactly towards the center. All right, take the tan phi is ay over ax. It's equal to that, which is equal to tan theta. Is it pointing in that direction or this direction? Well, so we already saw that it's pointing in this direction. And remember, tan theta is equal to tan theta plus 180 degrees. Okay. So phi is that. This is phi. So it's pointing exactly towards the center. Okay. I'm going to go 5 minutes over. I don't want to stop the lecture and then come back for 5 minutes. Okay, so. All right, so here's a curved road. You're driving along this road. Look at this. It has this component of the acceleration. What does that mean? What does this guy mean? You're speeding up. Okay, so if you're going in that direction, you're speeding up. And you have this component of the acceleration because the direction of your velocity vector is changing. When you're on a straight line path, you do not have this component of the acceleration because your direction does not change. Okay. And again, you're still speeding up, and you have this component of the acceleration because your direction is changing. All right, now what we want to do is the following. We will be interested in the following. Okay, so here's a person standing on the side of the road, and here's a person driving in this car at 60 miles an hour. Okay, so let's say if this dog was juggling in the car. What we want to see is, so this lady will see the dog juggling like that. What we are interested in knowing is, what does this lady see? So the dog is juggling inside the car.
She's a really fast dog.
You know that?
She's a really fast dog.
So what we're going to tell you is, so the dog is juggling, the object is going in a parabolic trajectory because gravity is the only influence. And what we'll see is for this girl, lady as well, it's also gravity is the only force acting on that object. So the ball is going on a parabolic trajectory as well, except that she sees it as a wider parabola. Okay, so we can do an easier experiment. Let's say I get on a skateboard and I go on a skateboard at constant velocity. I'm juggling a ball, and you'll see a wider parabola. All right, so that's what we're interested in. Okay, so here is the mathematics of it, and again, all right. So here's the position of the object. Here is the fixed frame. That's what she sees. And here is the moving frame. Okay, that's what she sees. Okay, so the position of this object with reference to the fixed frame is that there's the position of the particle with reference to that frame, and there's the position of that frame with respect to this frame. And when this is moving, this vector is changing. Okay. So you can see that RPS. Okay, what is this notation? The position of the particle with respect to frame S is equal to S prime, R is equal to RSS prime plus RPS prime. Okay, I'll rewrite this RPS prime plus RS prime S. Okay, so here's how you remember it. And again, you don't have to remember this. All I want you to do is remember the result, have a sense for it. This is the position of the particle with respect to the S frame. And then we introduced a new intermediate frame, S prime. So you can insert that letter S prime. Okay, just insert the letter in between these two guys. All right. Now you are calculus experts. You have these guys. You want the velocity of the particle, you just take the time derivative of this. So the time derivative of this gives you the velocity, time derivative of that gives you, okay. So now I'm calling this frame A and frame B. So velocity of particle with respect to frame A is equal to velocity of particle with reference to frame B, and then velocity of frame B with respect to A. Velocity of particle with respect to frame A equal to, okay. Again, all you're doing is inserting B in between these two guys. And then if you want the acceleration, you just take the derivative of the velocity. Acceleration in frame A is equal to acceleration in frame B. And as long as the two frames are moving at constant velocity with relative to each other, this will be 0. So whatever acceleration you see in frame A is the acceleration you see in frame B. Whatever acceleration she sees here is what she sees. And if the acceleration is gravity, then the trajectory is a parabola. Yep. All right, so here's one thing we're interested in. Okay, so let's say it's raining straight down and you're driving in this rain. What do you see? How do you see the rain? I'm sorry?
When you see the rain, like passing in the opposite direction.
So what you'll see is, you'll see the rain coming at you like that. Okay, so let's see that. Okay, so this is velocity of the rain with respect to the ground plus velocity of the ground with respect to the car is equal to velocity of the rain with respect to the car. Okay, that's funny. I inserted ground. This is velocity of the ground with respect to the car. Velocity of the ground with respect to the car is opposite to velocity of the, yeah. Okay, so there's the velocity of the rain with respect to the car, and velocity of the car with respect to the ground was that. So negative of that. And there's the velocity of the rain with respect to the car. Okay. All right, so again, you will need to remember this. Velocity of an object with some frame is equal to velocity of that object with reference to another frame plus the velocity of that frame with respect to that object. Okay, so all right.